So we'll get started here with what we want to do in today's class. So as a brief recap of what has happened in the previous class, we talked about the continuity equation. We saw how to drive that. Okay, and these are simple looking equations. Maybe it's a good idea for you to go back and sit down and look at it yourself. Make sure that you can drive it. Okay, so we are only going to follow Cartesian coordinates here, but there are other coordinate system. Okay, polar, cylindrical, cylindrical and polar are the same in the sense that cylindrical is a 2D version of this. Polar is a 2D version of the cylindrical thing. So there is no Z, r theta. When you use r theta coordinates, it becomes polar. Okay, when you have r theta z, it becomes cylindrical coordinates, and you have spherical coordinates where you have two angles and you have a radius, which is like mapping the Earth, for example. So there you need latitude, longitude, and of course you can have the distance here on Earth. The distance is fixed. We are on the surface of the Earth, so it's only the given radius. So there are two angles which are corresponding to latitude and longitude, which is what is used to pinpoint where our location, right? So that's the, so I mean, make sure that, I mean, so what I'm saying is that we are not sort of driving all the equations in all the other coordinate system, but I expect you to know or maybe figure out, sit down sometimes and figure out at least the simpler equations, okay? So that's the, so we had derived the continuity equation in cylindrical coordinates. I'm not going to keep on saying, sorry, in Cartesian coordinates every time. So I'm not going to say that we are doing it in Cartesian coordinates every time, but I've already made a general statement which is applicable for everything that we are going to talk about here. So the thing is that we have seen how to get to the continuity equation starting from the Reynolds transport theorem. Okay, and I hope that derivation is clear. Now the second thing that we did, okay, so what we got out of that, so the continuity equation that we got was dou rho dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. Now let me just make another generic statement. Okay, sometimes we do it, we have done all our derivation in 2D, but we may sometimes write the third term, the term in the third direction, sometimes we may just omit it. Okay, so you have to sort of understand the context, and if you're not clear, you can raise your hand and get it clarified. So this is the continuity equation that we have, and then we had the force balance of the Newton's laws, starting from the Newton's law. So Newton's law, of course, this is corresponding to conservation of mass. This is corresponding to conservation of momentum, and we had dou, let us say u dou t plus u dou x plus v dou u dou y plus w dou u dou z with a rho here is equal to dou by dou x of sigma xx plus dou by dou y of sigma, okay, let us just say xy here, or yx actually, plus dou by dou z of sigma zx, okay, plus a body force term. Rho fx is what we had written it as. Okay, so this is what we had derived in the previous class. I hope everybody is with me. Right, this is what we had derived in the previous class: conservation of mass, conservation of momentum. And there are two more equations. This is the x momentum equation. Similarly, you can have y momentum equation, and there is going to be z momentum equation. I'm not going to write down these equations, okay, but you can write it down by changing the variables. Now, what we want to do before proceeding is to figure out how many variables are there, what are the variables, and how many of them are there. Okay, so let me just sort of go ahead a little bit and just tell you what we are going to do in today's class is to drive the Navier-Stokes equation, which is the most important equation, as we know. And we are also going to understand where the approximations are going to come. What approximations are built in where. So the entire derivation process is very transparent, okay? And you have followed all that. If you have followed all of them, now we will start making that this is what is going to be applicable at this condition, and this is what is going to be applicable or not applicable under this condition, okay? So this is what we are going to do at some stage. So now what are the variables? You can look at these equations and say, what are the variables here? So you could start telling me and I will start writing it down. What are the variables? U, I heard U. What else? V and W. What else? Rho. Okay. Sigma XX. Sigma YX. Sigma ZX. And so on. So these are what you can see from here. As we said that the body force is typically prescribed for you. So that is not an unknown. Okay. So then you can see that those are the unknowns that we have in the equation. So how many of them? So first maybe you can complete our story with the stresses. How many stress terms are there? Okay, you can see that the left hand side will not lead to any additional variables, but the right hand side of these equations will lead to additional variables. So in total, if you look at the stresses, how many stress components will be there? 6, okay, 9 in general, but then we said that's because of symmetry, because stress tensor is always symmetric, that will reduce to 6. So we have 6 plus 4. So how many variables are there? Total of 10. Total variables is 10. Now, how many equations do we have? 4. So one is mass plus 3 momentum equations. So you can see that clearly the number of equations that we have is less than the number of variables, and we have a problem of closure. Okay, so this is what is known as the problem of closure, where the number of variables and the number of equations do not match. Typically, you will have lesser number of equations than the number of variables. Okay, other way around situation is probably never going to arise. Okay, I mean, you are going to be very fortunate. Then you can throw away one equation arbitrarily. Of course, all that means nothing. How do we get extra equations than the number of variables? That's over constraint system. So, so this is the type of thing that we have. Now, before even getting to how do we generate these additional equations, we can see the list and see what is included and what is not included. Okay, so what is missing from the variables? What are the variables that we typically think about, but those are missing from the list that we have as of now? Pressure. So missing variables, if I have to just write it down here. Anything else? And shear stress is sigma x. These are your shear stress terms, right? So we have not yet related that. Okay, so that's what I'm saying. So that's why I'm saying do it step by step. See what is coming where. Okay, so we will understand. See, you can now see where these are coming from, right? So there is no confusion, and you can see whatever is the assumption which was built in obtaining them. That's assumptions that where these equations will apply. And what are those conditions? We said essentially what are the conditions under which these have been derived? Essentially, it's Newton's law. Okay, so we are not really making any approximation. Of course, we can say we are not looking at relativistic effects and such things. Okay, so those are totally beyond the scope. But otherwise, wherever Newton's law applies, these equations apply, right? So there is no approximation built in as such. What about this equation? Again, there is no approximation here. We are essentially based on it on Reynolds transport theorem, okay, with no approximations. Okay, so this is expected to be an exact equation. This is also expected to be an exact equation. Okay, but now at this stage, now the assumptions will start coming in. So that's why you have to understand where till what is exact and what is not. Okay, and why do we need to bring in those inaccuracies or those models or approximations? I mean, they go by different names, but so one thing you can see is variable is missing, is P, okay, and you can say T is missing, temperature is missing. There is no reference to temperature in any of these, right? So if we have to understand T, where will T come from? So T will come from the energy equation. So we have not written down the energy equation, so T is not appearing for us. Okay, so that's, you can say that, and we are, let us say, in this course, as far as this course goes, we are not interested in energy equation. Okay, maybe we will have half lecture, one lecture on getting to the energy equation, but if time permits, but otherwise we don't have to talk about temperature in this course. Okay, so you can still see that the pressure is missing. Okay, this is just to keep in mind that in all these cases, everything we are saying is exact, but pressure is not appearing for us. Okay, that's one point that we can take home. The other point is that the number of variables and number of equations are not matching. In fact, we have far more number of variables as the number of equations. So what we have to start doing is to write out, so we have to start generating additional equation. Now let me ask you one question. Where in this assumption, in this writing down these equations, have we assumed that whether we are working with air or water or blood or some other fluid? You can see that we have not appealed to what type of fluid that we are working with, right? So that is not there. Okay, so this is now what we have to bring in. Okay, and when we bring in, that will generate the missing equations that we are talking about here. Okay, so those are what is known as constitutive relationships. So you can see that this is exact, but constitutive relationships are not exact. They are something which has been derived empirically. Okay, so you look at experiments, you see how these different fluids would behave, and then you try to relate these stresses to something that you are going to see. Okay. Okay, any questions here? Okay, so we are going to write out constitutive relationships now. And we can see that now we can, if I look at the variables in the stresses, you can see that there are two types of stresses. One, which are your normal stresses, and the other one, which are your shear stresses. So I need to write out separate. So you can think of that these are separate. They have different action, different type of action on the surface, or your object or your fluid, or other in this case. So therefore, we are going to have to write different type of equations for the normal and the shear stresses. So let us write out for sigma yx. Okay, so how is this going to get related? So this is a stress. Now we can go back to solid mechanics. We have, I'm sure, read enough of that. There again we talk about stress and strain. Here we are going to talk about stress and strain rate. There we say that they are directly proportional or related to each other, directly related to each other. Here we are going to say the same thing. Okay. So gamma dot xy, rather let's keep the same subscript. Okay, and the proportionality constant here now becomes my mu. Okay, so this is where now the viscosity is entering, and viscosity is now bringing in information whether I'm talking about air or water or some other type of fluid. Okay. So this is, and once we write it down, we can see that similar type of a relationship applies to the other stress components as well. And what is this term here? Now, if you look at the deformation of the fluid element, this is where we had derived this. So what is this term? Yes. So dou v dou x plus dou u dou y. Okay. Now let me again remind you one thing. When we talk about stress, we think of dou u dou y. Okay. Please don't make this mistake again. Mu times dou u dou y is what you say. What you see here is there is an additional term. Okay. That term is dou v dou x. It may happen when you're talking about shear stress on a surface. So, okay, we say that, okay, this is my velocity profile, okay, and therefore the shear stress is mu times dou u dou y. Okay, but you can see that this is fine for this surface, but what about this? Okay, let us say that the flow is happening on top of this surface. So in this case, you can see that there is a dou u dou y with the mu term. What about dou v dou x? So for that, you'll have to look at this point and this point. Is there a change in the v component of velocity between these 2 points? This is my x direction. This is, of course, my y direction. So is there a change in the v component of velocity? Yes, there is. Velocity is 0 here, velocity is non-zero here. So there is a change in velocity v, okay, between these 2 points, and therefore this term is also present. This term is also there. So don't make that mistake and just say it's mu times dou u dou y. Okay, it's mu times dou u dou y plus this term. And if you keep this this term in mind in general, okay, you know that in this particular case, in both these 2 points, v is 0. So there is no change in v with the change in x. So dou v dou x is 0. Okay, so it reduces to whatever we are saying here. But in general, this is not true. Okay, got it? So these are some fine points that we need to know. And we know that if this relationship applies, we call them as Newtonian fluids. Okay, and this is very different from the Newton's law that was relating motion. Here we are relating stresses to rate of strain. And we are claiming that, or what turns out, that there is a linear relationship between the two of them. Linear and passing through the origin. Okay, and this is just, so if I look at stress versus strain, this is sigma yx, and this is my gamma dot yx. Okay, so then this is the type of curve that I'm looking at. Okay, I'm not looking at this curve or this curve or this curve even. So there is a non-zero intercept here. Okay, so this is what is covered in the homework that has been given. So you have to look at what are the other ways when this relationship does not apply. How do we model those fluids? So this, in the interest of time, we are not going to cover it in the class, and we have left it as a homework for you to read. So now it comes to sigma xx. What about sigma xx? This turns out to be a more tricky thing to answer. What is sigma xx? Okay. Before we get to that, any questions here? So to get to sigma xx, we are going to appeal to solid mechanics. Okay, and we are going to see whatever happens in solid. Okay, we are going to have a counterpart of that in liquids or in fluids. Okay, so just like in some sense you are saying that I'm appealing to solid mechanics here and saying there is a linear relationship between the two of them. Okay, I can say that there is a linear relationship between the other two. So now let us think of a rod. Okay, and let us say that this is just stretched. Okay, there is a force which is applied here. Okay, and we know that force, if I divide it by area, I will get sigma. So let me just work with sigma xx. So what will I get as epsilon xx? Yeah, sigma xx upon E, some elasticity, correct? Now what about epsilon y? So this is first of all, so the rod will stretch in the direction of the force. What about the other two directions? It will contract in the other two directions, right? And how much will that be? Minus nu times sigma xx by E. And sigma epsilon zz is minus nu sigma yy upon E. Right? So we know this. Now let us say all the three stresses are, this is a very specific case where I'm applying force only in one direction. Okay, now instead of that, let us think of that I apply a force in all three directions. Then what are the stresses that I'm going to get? Who's going to tell me that? So can I just use this information to write out? I will just remove this. Okay, maybe I can go to the other one. Yes, what is sigma xx in this case? Sorry, epsilon xx. Let us write it out for epsilon xx. So just like you can see that if I apply a sigma yy, I will get an epsilon xx, which is going to be with a minus nu upon E terms, correct? Similarly, if I apply a sigma zz, I will again get an equivalent term like this, like these terms here, right? So if I apply all three, I have to superimpose minus nu times sigma yy upon E minus nu times sigma zz upon E, correct? So now let us add and subtract one term. So I get, let me also write out this with a nu. So sigma xx upon E times 1 minus 1 plus nu minus nu sigma xx upon E plus sigma yy. Let me take nu by E common, nu by E common, sigma xx plus sigma yy plus sigma zz. Okay, so all I have done is added and subtracted this term. I've added this new term, nu times this term here, and I've subtracted it. So I've not changed the equation. Now let me define a sigma bar, which is going to be sigma xx plus sigma yy plus sigma zz upon 3. So I get epsilon xx is equal to sigma xx times 1 plus nu upon E minus nu upon E times sigma bar. Okay, everybody with me till this point? Yeah, 3 sigma. Thanks. Yeah, thanks. Okay. So what is my sigma xx? I can write it out from here as sigma xx is equal to, so okay, we can just do it in 2 steps if you want. So E upon 1 plus nu times epsilon xx plus 3 nu upon 1 plus nu times sigma bar, correct? This is what we are getting here. Now what we are going to do is introduce G in there, the shear modulus. Okay, we know how does it get related. So it is E upon 2 times 1 plus nu. So that means that I can write sigma xx as 2g times epsilon xx plus 3 nu upon 1 plus epsilon times sigma bar. I hope everything is correct here. And now what I'm going to do is further write out, split this term as 2 terms. One will be a sigma bar, and what remains from here will be 3 nu minus 1 plus nu upon 1 plus nu times sigma bar. So what remains is, what I'm getting is the sigma bar times 2 nu minus 1 upon 1 plus nu. So this is what my sigma xx is. Everybody with me? Everybody with me? We have not really done a whole lot other than by saying that once we understand this, okay, we are just saying that if I apply all the 3 stresses, I will not just get elongation because of sigma xx along the x direction, but I will also have contraction because of the sigma yy and sigma zz term, and they will be in this amount. Okay, so the total I get is this. Okay, and then I just add and subtract one term. Okay, I get because I want to have the summation of all the 3 stress terms coming out, which I replace it by the sigma bar. Okay, so I'm just writing it out like this. Okay, and then I'm making my sigma xx as the subject of the equation. Okay, so I just change the variables from epsilon to sigma. So this is what I get. Okay, and then I realize that this relationship is available to me. So I use that. Okay, and I get here to G, and finally I split this term into 2 terms. Okay, for convenience, and we will see why exactly that is done. Okay, so this is essentially what we have done till now. Yes. This term, here. Okay, so it's okay. So if you want sigma bar here and a sigma bar here, and this term is in the bracket. So essentially, I've taken out 1 sigma, so I have to subtract out. So 1 sigma divided by 1 plus nu was there. So I have to subtract that from this other term. So I will get 1 plus nu in the numerator. So I get whatever has been written here. Okay, so this is one sort of an equation that we get. Now we go back to our starting point. Okay, and our starting point was this. Okay, now let us say that I can write out similar equations for the other 2 directions. Maybe just let us go to the other board. So from the equation which is given on the top left, okay, so if I have to write out a similar equation for epsilon yy and epsilon zz, I can write it out in a similar manner, not an issue. Okay, but then I add up the 3 equations. Okay, so I write out an equation for epsilon yy, okay, epsilon zz. I'm not going to write out these equations. You can complete that exercise yourself. And then I'm going to add up these 3 equations. So what am I expecting to get? Epsilon xx plus epsilon yy plus epsilon zz. So what do I expect to get? Sigma xx plus sigma yy plus sigma zz, okay, into, so I will expect to get sigma xx plus sigma yy plus sigma zz and divided by E and multiplied by 1 plus nu. Okay, and for the remaining, I will get minus 3 nu upon E sigma xx plus sigma yy plus sigma zz. Correct? Everybody with me? So the good thing now, which has happened, is that these two terms are the terms in the bracket. All these sigma terms are common. So I can take that as common terms. Okay, divided by E, which is also common. And I get 1 plus nu minus 3 nu, which is 1 minus 2 nu. Okay, so I get from here, okay, so if you want, we can just go back to this and write out in a similar manner. If I write it out first epsilon yy, what will I get? So I will have to replace sigmas in the first equation. The other term will not change. Okay, so that's why, and similarly, I will get a similar term for epsilon zz, and then I can add it up. So the first term would have contributions from all the three terms. So it will become sigma xx plus sigma yy plus sigma zz, and 1 plus epsilon upon E will remain common. And the second term will have all these three terms like this, so which will add, so will give me a 3 here. So I think this is correct. Okay, and then I just take out sigma x, this term in bracket, as common, divided by E, which is common, and then I just add up the other. 1 plus nu will not come, it will be there, no? 1 plus nu is here. Okay, anyway, you can go back and check that. Okay, I don't think there is a mistake here. Where is the problem? Where is the issue? Sigma yy. Yeah. So this is correct, right? So now if I write it out of epsilon, let us just write it out. So epsilon yy, how will I write it out? This is the only term which will change, sigma yy upon E 1 plus nu. And this term is not going to change. Correct? And similarly, if I look at epsilon zz, again, this has to be replaced by sigma zz upon E times 1 plus nu minus nu upon E times sigma xx plus sigma yy plus sigma zz. Okay, and again, where is this coming from? Why this term is not changing? Is essentially from whatever we have done here. Okay, now I'm adding, what I'm saying is add up these three equations. Now the equations are in front of you. So add these terms. So here 1 plus nu upon E is common, and sigma xx, sigma yy, sigma zz get added up. So this is what we have done here. Okay, this is what we have done here. 1 plus nu is common, or 1 plus nu upon E is common, and we add up the other three terms. And here these three terms will get added up. So I will get minus 3 nu upon E times all this. Okay, and then I'm writing it out as with sigma xx and upon E is common, and 1 minus 2 nu is coming out. So what we can see now is, why did we do all this, and why did we do this? Because here earlier we had 2 nu minus 1. Okay, so this is what we were getting, and you can see that that can be eliminated. So let us say that this is one major equation that we have, this is the other major equation that we have, and then we combine them. Okay, so this one I get from here, I get sigma xx plus epsilon yy plus epsilon zz is equal to sigma xx plus sigma yy. This term is anyway 3 times sigma bar, 3 times sigma bar, okay, and then divided by E, and then 1 minus 2 nu. So I get sigma bar as E upon 3 times 1 minus 2 nu times epsilon xx plus epsilon yy plus epsilon zz. Okay, so this is what I'm going to substitute in here. Okay, I think there is 1 plus nu. Okay, let us just substitute and see what is it that we are getting. So if I substitute this equation, so first of all, any mistakes I have made or any questions that you have before moving ahead? So these are the two major things that we have, and we're going to use them, and hopefully we will have what we are looking for. So basically what we want to do now is substitute this sigma bar in here, and in fact I see that 1 minus 2 nu is also common. So I get sigma xx is equal to 2g epsilon xx plus sigma bar plus this sigma. I'm going to substitute this sigma into 1 minus 2 nu essentially, which is this sigma into this part here, which I'm going to substitute here. So I will get with a minus sign, and it is going to be E times epsilon xx plus epsilon yy plus epsilon zz upon 1 plus nu, which is showing up, and there is a 3 here, which is a 3 here, 3 in the denominator, which is also showing up, right? Something is not entirely correct. Okay, so now we can replace, so this is fine, yeah. So now we can replace this with a g here. Okay, so I think that's our last step. 2g epsilon xx plus sigma bar, and now you can see that E upon this 2 plus is equal to 2g. So I'm going to replace this with a 2g on 3 times epsilon xx plus epsilon yy plus epsilon zz. So this is the equation that we are actually looking for. So this is the final equation that is of interest to us. Okay, any questions here? So again, we are just using the fact that how the stress and the strain are related. Okay, if I have to just recall very quickly, so we said to take a rod, stretch it first in the one direction. You see that you don't have just stress generate epsilon x, but you also generate epsilon y and epsilon z. Okay, and then therefore, if there are stresses in all the three directions, you can add up the three things. So you get epsilons like what has been given here. Okay, and then you do a series of manipulations. This is what you get for sigma xx, and we also get, if I add up these three equations, this is the other equation that we get, and we use these two relationships to get to this point here. Okay, so now what we are going to say is, what is my epsilon xx? So we have already done deformation of a fluid element. The same thing, the deformation of a solid element can be done, right? So there you will get, you got dou u dou x, right? This is what we had gotten. So you can see that this term will represent deformation in the case of solids, and in this u is going to represent velocity in the case of a fluid. It's just the rate of deformation, which is what we are talking about here. Everything becomes a rate term here. Okay, so that we'll come to that, but we can see that the epsilon xx is nothing but this. Similarly, if I look at epsilon yy is going to be dou v dou y, and epsilon z is dou w dou z. So this is what we have, and now we can come to this equation, substitute them. These sigma xx is 2g times dou u dou x plus sigma bar minus 2g upon 3 times dou u dou x plus dou v dou y plus dou w dou z. Okay, so all we have done now is substituted these epsilons with the gradients and in deformation. We are still in the solid phase, or we are still looking for solids. So we are looking at deformations along the 3 directions. Okay, so this is what we have at this stage. Okay, so this is what we are interested in. Now at this stage, we will now go from, we'll say that, okay, if this is what applies to solid, okay, a similar thing should apply to for fluid, okay, and in an analogous manner we can do it, okay. Maybe it is not, it is easier to see it in solid that we are applying in the x direction and we have contraction in the other 2 directions. It is much easier to sort of relate to a solid, and therefore we start with the solid and we drive this, okay. But we can say that the same arguments would apply for a fluid element as well, okay. So we can now say that I will replace this G, so from solid to fluid is what we are moving. So what we have to do is, there are 2 things. One is G, which is going to be replaced by mu. Okay, so whatever shear, so this is also looking at shear modulus. So this is also an equivalent of that in fluid. So that makes sense. I replace these. And this sigma is now going to be replaced by pressure. This is now pressure makes an entry. Okay, so you are saying that whatever is the sum of all the stresses that you have in the 3 directions, that is what your pressure is. Okay, so this is how you replace, and of course u, instead of being deformation, so from deformation we are going to velocities. So you can see now that sigma xx for fluids is equal to minus p plus 2 mu times dou u dou x minus 2/3 mu times dou u dou x plus dou e dou y plus dou w dou z. Now here when we are talking about in fluids, okay, we have now introduced our viscosity, and these are now our velocity components. Viscosity has been introduced, and the velocity components are what is involved in these. The gradients of those are getting involved here. Okay, now I will pause for questions here. So this is a very major sort of a bridging. So you can now see that we have essentially generated 6 equations, one for shear stress and one for normal stress, but then we know that a similar thing can be done in the other directions. There is no preference why whatever we have argued should only apply in along the x direction. Same thing can be done along the y and the z directions. Okay, so we will get equivalent or similar sort of looking expressions for them, or we can think of, sometimes we think of that we replace u with v or x with y and so on. So there are some transformations like this. So once you have an equation, you can just transform, you can change the variables and you have the new equation coming out directly without having to do anything. You just have to understand what will get changed to from what to what. Okay, questions here? Yes. Right. Yes. No, so we have derived it. Now you can see. Okay, we have not done anything. We have not said anything about compression or elongation. Okay, we have not made that statement anywhere. It's just coming from. It's just natural from here, right? So did we? So okay, yeah. So here, yeah. So you are right. So here we are saying that pressure is always compressive. So this sigma we are replacing it with the minus p. Yeah. So I should clarify that. Thanks. Yeah. So otherwise you had a plus sigma. Now the way to think about is that if I set the velocity to be 0, okay, if all my velocity is 0, okay, so all these terms go away, okay, but you know that in fluid you will still have a pressure force which is acting on it and which is going to be compressive, and therefore this term has to survive, or this is where what is getting accounted for there. Okay. So now what we have done is, and viscosity is where, as we have already said, is where the information about the fluid is coming in. Now, where is information about, so now, as we said, we have sort of completed our derivation. Now we can apply, substitute these equations into our equations that I had written in the beginning of the class, which was your Newton's law or the conservation of momentum equation. So your sigma, all your sigmas are now known. You can substitute it and you will get the Navier-Stokes, which we will do in a minute. But before that, we will just pause here and see what is it that we are saying, okay? Because this is in that sense a very, very important class to understand what we are keeping and what we are neglecting, okay, in our equations, and why and where is being done exactly. So this whole process I've just tried to make it, or my narrative, I've tried to give you a narrative where you can see these points very, very clearly. Okay, there are alternate ways to drive these equations, but what I find in this narrative is that you can see what is coming where and why. So what you have said is um, where is now fluid is coming in, fluid property information about whether it's air or water is coming in through viscosity, one. Now whether it is going to behave as a Newtonian or a non-Newtonian fluid, where is that coming in? Through our stress term, okay? We said is a linear relationship between the stress and the rate of strain, okay? If it is non-linear, okay, and other models which we have discussed, which we have left for the homework or the reading assignment, okay, you can find out where exactly the other models will come in, how they come in. So as of now, what we have not talked about is compressible and incompressible. Okay, so you can see that whatever we have done here is all applicable for compressible, because incompressible is a special case of compressible. So compressible is a bigger set, and incompressible is a smaller set from there. Okay, so as of now, we have not said anything about compressible and incompressible. Now we are going to get to that point. Okay. So we will just make a box around this because this is an important equation that we have. And we are now going back. So constitutive relations have now been found. So now let me just get into compressible, incompressible. Okay, now when we talk about compressible or incompressible, it is always related, it's a flow property. It is not a fluid property. Okay, and what is the difference? Okay, can the fluid be compressed? Okay, that is if you're talking about the fluid be compressed, then you are talking about a fluid property. Okay, but when we are saying that can the flow compress or change the density in the flow, then we are talking about a flow property. Okay, so here we are talking about a flow. Because of the flow, can there be a variation in my density in the various regions of the flow? That's what we mean by a compressible flow. So we go back now. So we have to the equations that we had, the mass conservation equations. So for incompressible now, we are going to say that rho is constant. Okay, so this is how a incompressible flow is defined. Incompressible flow is where the density is constant in the flow. If the flow of density is constant, it is an incompressible flow. Okay, does it have anything to do with Mach number? You can see that we have not said anything about the Mach number. Okay, so don't get confused there. Okay, so what we say is if the Mach number is large, the flow is compressible. But that does not mean that if the Mach number is low, the flow is incompressible. That is not implied. Okay, so what we say is a one-way relationship. We say high Mach number flows are expected to be compressible. But we never say that low Mach number flows are expected to be or are incompressible. No. In fact, they are not, and there are situations where we will talk about them. Okay, so what is important is the incompressible flows are, again, density has to be constant. Now, if density is constant, then I can look at this equation, and this equation simplifies to so I can get rid of the first term, I can take rho out of each of these equations, and then rho is, I mean, because this term is not there, rho taking out, and then rho can be removed. So I get dou u, dou x, dou v, dou y plus dou w, dou z is equal to 0. So this is the equation that we get for incompressible flows. Okay, so as we said, now incompressible flows apply or means that density is constant. Don't make that mistake of saying it is related to Mach number. Okay, it is Mach number can give you some information, but that not the complete information. So now we can discuss when can this scenario happen, that this equation has to be applied and not this equation. You can see that what can happen. Velocity is being large, it's not very visible, it's not very clear why velocity being large will lead to these terms being non-zero. So we will not talk about that condition. But what you can see very clearly is this term. Okay, when can you get rid of this term? Can you get rid of this term? Okay, because if you cannot get rid of this term, okay, even if you take rho out, rho is not a function of space. Okay, you can take rho out of this equation, but you cannot still get this equation here because there is d rho, dou rho, dou t sitting here. Okay, and when can this term be non-zero? Physically, when density is varying very rapidly. So if you have a very high oscillating flow, okay, your density may not be constant, this term may not be 0, okay, and the flow will not necessarily satisfy this condition. Okay, so you can see that this is one condition right away that you can see that when this term cannot be removed. Okay, so high frequency flows can become, they can be very low velocities, but high frequency flows can become compressible. Okay, any questions here? So this is one change that we see when we go from this is a compressible, as we said, everything is compressible because we allow for density to vary. But now here we are saying that it could be incompressible, and we apply a much simpler equation. Now there is a very, now I would like to draw your attention to this equation, the constitutive relationship that we have derived. Now what happens here when we go from compressible to incompressible? So you can see that right away that this last term now is 0. Okay, because of this condition here. Because if it is incompressible, then this equation will reduce to, for incompressible, sigma xx is becoming minus p plus 2 mu dou u dou x. So it's a much simpler looking expression that we have here. Correct? So again, let me, just like we said that when we apply shear, we should not forget about the dV dx term. Okay, when we look at normal forces, we say pressure is a normal force, but is the pressure normal force? Again, the equation is telling you. What are you missing? If you just say pressure is your normal force is only pressure, you are missing this term, right? And of course, if it's a compressible flow, then you're missing this entire term. Most of the time, you can get away with this because this term, contribution of this term turns out to be small. But we can see that we are making a mistake. That is not what you should be looking at. Okay, as far as you are doing it with understanding is fine. Okay, but without understanding is where the issue is. Okay, so when you are looking at normal forces, don't forget about You just don't consider pressure. You also have to consider this term. So now we can go back to our conservation of momentum. By the way, are there any questions here? Or maybe any questions here? I heard somebody saying something. Now we go back after the entire. So we have shown you the derivation, no, where it is coming from. So this was your epsilon xx. If you go back to just remove the solid part. So this was your 2g, and this was your sigma xx. Correct? This is what it was. Now g was related to E, right? So then you can see that your sigma xx was depending on, so epsilon xx was depending on sigma xx. Okay, it was also depending on if there are other stresses. Okay, the other stresses are contained here. This was your sigma bar. Okay, so it's the same thing, no? We have just changed our language, but the information is the same. Okay. Okay, so now we will go to our, oh wow, it's almost time. Okay, so we will very quickly look at, okay, we'll just look at the right hand side first because we don't have time. So we can write out the sigma xx as given here, sigma yx as given here, mu times do v do x plus do u do y, sigma. So if I look at the right hand side of the momentum equation, we will do everything in the next class, but let me just make a few points before we, last 2 minutes that we have here. Okay, we have 4 minutes. So we are going to have sigma derivative of this. So minus, so we had sigma xx plus dou by dou y of sigma yx plus dou by dou z of sigma zx. This is what we had on the right hand side, plus body force term, rho times fx. So we can substitute. So one thing which is very clear, that what type of derivatives or what order of derivatives will get involved here. Okay, there is a first order stresses here, and we said that stresses do not lead to a, stresses do lead to a force, but they do not lead to a net force. What lead to a net force is the gradients, right? So you have to take the gradient. So these are your only stress terms. So you have to take a gradient of them to lead to a net force, okay, which is what will enter into your momentum equation. Okay, so then that means that these terms will become, this term will become a second order derivative of u with respect to x. Okay, so that's where the second order terms on the right hand side will start showing up. Okay, so what we can do very quickly is just look at these things. Okay, let us substitute the first equation. So I get minus 2 by minus dou p dou x, dou p dou x plus 2 dou to u dou x2. See, in general, mu could be a function of space as well. Okay, so mu, okay, now, okay, maybe that's, so is mu really a constant? We have already discussed that. What can mu depend on? It can depend on temperature, pressure, gamma dot. Okay, so it can depend on all these three things. So what are these scenarios? Let us just recall them. We have already discussed them. Is viscosity a function of pressure? Yes. We said for gases, for example, we know that it is not a function of pressure, although it could be expected, but it turns out that viscosity is not a function of pressure. So essentially, it leaves us with only temperature. So can it be a function of temperature? It can be, and we have seen that it can be a very strong function of temperature. Okay, so what have we said about temperature? We have said that we are not considering temperature variation. We are not bringing in the energy equation, and we are not doing a balance of energy in this case. So temperature is not going to show up. Okay, so in otherwise, if you are talking about heat transfer, okay, then you have to worry about viscosity becoming a function of temperature, and temperature being a function of space. Okay, viscosity becomes a function of space, or can in general become a function of space. Right? You understood? Now, what about gamma dot? Can it become a function of gamma dot? Viscosity itself becoming a function of gamma dot? We have said Newtonian fluid, it's a constant. It's not a function of gamma dot. But once we are talking about non-Newtonian fluids, let me just make that last point here before we close. So if I plot tau yx, gamma dot yx, okay, we have now seen that they are linearly related, and this slope is your mu. Okay. Now, if I look at this curve, you can see that the slope is still mu, but now the slope is changing. Okay, so you can see here in this case, mu is some function of gamma dot xy. The slope is some function of gamma dot xy. Okay, here for a Newtonian fluid, it's not a function of gamma dot xy. Okay, so what we are saying now is, if you are talking about an isothermal situation, then my viscosity, and we are always going to limit ourselves to a Newtonian fluid. So therefore, we are not going to see that mu is a function of any, or not a function of, it's a constant. So that means that when I take a derivative of this term here, I don't have to consider mu as a function of space. Okay. So let's, somehow I was thinking it's 56 here. Okay. Sorry about that. Okay, so we will substitute these terms in these equations and see what is it that we get. So we get minus 2 by 3 mu. And taking a derivative gives me dou to u dou x2 plus dou to v dou x dou y dou by dou x dou z. So this is what I will get from my first term. This is just the first term that I'm writing. Okay, plus the second term, if I write it out, I get dou by dou y of dou u. Okay, and of course, everywhere there is a mu here. So let me just mu times dou to v dou x2 plus mu times dou to u dou x dou y plus mu times dou to w dou x2 plus dou to v dou to u Okay, so this is what I'm going to get from the, if I substitute all these terms in here. Okay. Are we clear about this? All we are doing is substituting the stress terms that we have found, okay, into the momentum equation now and trying to get to the Navier-Stokes equations. Okay, so if you're talking about, instead of talking about a compressible flows, we are talking about an incompressible flow. So you can see that in that case, this term will be 0 right away. This term will not appear. Okay, because this term is anyway derivative of this term, which was 0. Now, what about the remaining terms? So I will not carry forward this term. And we say that the right hand side is equal to minus dou p dou x. And now what I'm going to do is take certain terms. I'm going to divide this term into two terms, mu times dou to u dou x2 plus mu times dou to u dou y dou x2 again. So I'm doing it now for an incompressible flow. And from the other terms, I get dou to v dou x2 dou to, sorry, this, yeah, dou x2. I think we have messed up certain terms here. Yeah, I think we have messed up. Okay, so I think we have messed up. Sorry about this. So this equation is not correct. This equation is not correct actually. So this should have been a y square here. And this should have been a z square here. And the other term is correct. So we should have been taking the derivative of this term with respect to y. Yeah, so we should have taken the derivative of sigma xy with respect to y. So this is what I would get. And if we have to take the derivative of this sigma with respect to z. So I had taken everything with respect to x, or some mistake I had made. So I hope this other term is correct, right? Okay, so let's just, I think we, instead of trying to skip steps, let us just do it, all the terms in there. So this is dou by dou y of dou u dou y plus dou v dou x. Okay, so from here we get dou u, okay, dou u dou y square and dou v and dou x dou y. Similarly, here you will get this and you will get a w here. Okay, so now it is correct. Now there is no mistake. We are just trying to skip one step has led to this issue. So the right hand side is okay. So we have to just write out everything correctly now. This is dou u dou y square. This is dou v plus dou by dou v. Of course, everything comes with a mu, so mu is common, and d2 v dx dy plus dou to u dou z2 dou w dou x dou z. Okay, so finally we have gotten the right thing. I think we just made too many mistakes. So the right hand side now will become dou p dou x plus mu times dou to u dou x2 plus dou to v dou to u dou y2 plus dou to u dou z2. Okay, and the remaining terms can be written with dou by dou x as common and dou u dou x plus dou v dou y plus dou w dou z. Okay, so I'm just writing this term, and this term, with a derivative. So there is a derivative with respect to x. So I take that as common and write out the other terms. And this term has all u's, and so I just take everything together. Okay, now we can see that this term again is 0 from continuity because we are doing it for an incompressible flow. Okay, if we were not doing it for incompressible flow, then of course this term is going to be surviving or may survive. And along with that, we would have this term also in there with us. Okay, so what you can see is that if I go back to our momentum equation, the right hand side is changing substantially between a compressible flow and an incompressible flow. Okay, whereas if you look at the left hand side, what happens to my left hand side? The left hand side was mass times acceleration. Okay, there is there any change? No. Okay, so this is the sort of the interesting part. Sorry, body force. Okay, yeah, so let's write the body force. So if I look at the left hand side, so left hand side of the equation was simply this, which was written as rho times dou u dou t plus u times dou u dou x plus v times dou u dou y plus w times dou u dou z. Okay, so you can see that this row stays outside. Okay, and this is staying outside because we said it is no, this is not incompressible. This left hand side, we just simply said it is mass times acceleration, and we said the mass is not changing. Okay, because we are not considering the scenarios that we have talked about, which are phase change, chemical reaction, or the thermonuclear reaction. Okay, so that is why we are not putting mass inside. Okay, that's what is driving out this density outside. Okay, so once the density is outside, it's going to stay outside. Okay, so normally what happens, I'm just emphasizing this point, is because sometimes we say when it's a compressible flow, okay, between compressible and incompressible, that's what we are looking at. So when we try to take compressible flow, we just take the left hand row inside and we say that's my compressible flow, and the right hand side does not change. Whereas what we are saying here is very clearly that the right hand side, the stress terms are the relation between stress and strain, okay, will change. Okay, so the right hand side will change, but the left hand side is not going to change here. Okay, so we will come back to this one point again and emphasize this so that we understand where is compressible and where is incompressible assumption coming in. Okay, so I think this is where we will finally stop after saying several stop. But so this is where we are finally stopping. So what we have done is a very brief recap. Is we have looked at the constitutive relationship. We have then seen where the assumptions of Newtonian versus non-Newtonian is coming in. We have also seen where the assumption of various types of fluids which is coming in through the viscosity, where the information about compressible versus incompressible is coming in. And once things are incompressible, we do see a lot of simplification in terms of our constitutive relationships. And even when we substitute those constitutive relationships into the momentum equation, again there is further simplification. Okay, so this is what we have seen in today's class. Next class, we will actually write down our Navier-Stokes equation with all the terms that we have found, substituted into that momentum equation so that we have the complete form of the Navier-Stokes with us. Okay, so this is where we'll stop here. Thank you.